The Tsubame 4.0 is a world-class supercomputer at the Institute of Science, Tokyo. It delivers a peak performance of 66.8 petaflops. The Tsubame series has always demonstrated a strong presence in the world of supercomputers, where development is highly competitive. The latest version, Tsubame 4.0, first went into operation on the Yokohama campus in April 2024. Its concept is a supercomputer for everyone. As a supercomputer for everyone, which boasts overwhelming compute power but can be used easily by anyone, it supports R&D that meets the diverse needs of society and the era. One day, you might be involved as a user or even as a developer. The path is open. Now, through the Tsubame 4.0, let's unravel what a supercomputer is and what it is capable of. A supercomputer connects multiple computers to achieve extraordinary computational throughput. In science and engineering, there are discoveries you can only reach after running truly enormous computations. This is where supercomputers come in. Imagine a calculation that would take 1 year on a normal computer, but finishes in 1 day on a supercomputer. Even if the answer is the same, the quality of the research is far different. Quantity impacts quality. That is the power of a supercomputer. The creation of virtual reality requires continuous computations of space, perspectives, and the relationship among objects, all on the same timeline. In recent years, the rapid popularization of AI technologies has brought about major breakthroughs through huge numbers of computations in parallel. The high speed of a supercomputer comes from doing many calculations simultaneously. Supercomputers have evolved by improving how they perform parallel processing. Supercomputers are made up of machinery components called hardware and control mechanisms called software. First, let's look at the hardware. In the early 2000s, specialized CPUs were designed for each supercomputer on national-scale projects. At that time, supercomputers adopted a configuration called vector processing, which achieves parallel processing within the CPU. With later supercomputers, the most common structure was scalar processing, a large-scale parallel configuration encompassing the system as a whole that uses general-purpose CPUs while minimizing manufacturing costs. Current supercomputers use a hybrid configuration that combines CPUs and GPUs, and structures designed to increase the efficiency of parallel processing have been broadly adopted. GPUs were originally developed for video processing, which requires high-volume computations. At the same time, they have exceptional capabilities when processing thousands of computations in parallel, and demonstrate superiority in massive data processing, as in the case of AI and simulations. Tsubame 4.0 combines 2 CPUs and 4 GPUs in each node. Both CPUs and GPUs execute calculations based on orders, but their configurations differ. CPUs place a greater emphasis on circuits that execute control and decision-making, while GPUs emphasize circuits running the same kind of operation across many data elements at once. For this reason, CPUs are geared toward complex computations requiring various conditions and case distinctions, while GPUs are suited to massive amounts of computations under the same conditions. Combining CPUs to handle computation quality and GPUs to handle computation volume makes it possible to dramatically increase performance compared to existing CPU-only systems. Computers have been evolving rapidly, and supercomputers refer to computers with a higher computing capability than computers of the same era. Each year, supercomputers continue to evolve in terms of both configuration and performance. Now let's look at the basic performance of Tsubame 4.0. The CPU is the EPYC 9654, AMD's top-of-the-line processor for servers. Each node contains 2 CPUs, and each CPU has 96 cores, so computations are processed with a total of 192 cores running simultaneously. Tsubame 4.0 integrates 4 NVIDIA H100 SXM5 GPUs. The H100 is the representative data center GPU for the era of AI, and in the Tsubame 4.0, it adopts a configuration with a massive 94GB memory. By selecting this CPU and GPU, Tsubame 4.0 achieves aggregated performance of 66.8 petaflops in double precision and 952 petaflops in half precision. This overwhelming computing capability is equivalent to thousands of general-purpose home computers. Next, we will look at the storage and system configuration of Tsubame 4.0. The supercomputer performance is influenced not only by compute itself, but by how fast the data can be read and written. Tsubame 4.0 has adopted the HPE Cray Cluster Store E1000 for storage. It can store 44 petabytes of data on the hard disk base and 327 terabytes on the SSD base. By combining HDD as a warehouse to store huge volumes of data with SSD as a workbench for rapid input and output during calculations, massive amounts of data can be handled without delay. All of this is housed in 30 racks in total, 23 racks for compute nodes and 7 racks for storage and system management. The system was built by Hewlett-Packard Enterprise. There are 240 compute nodes in total, with a total of 960 GPUs. At this scale, the configuration enables concurrent execution of massive computation and data processing. Supercomputers generate enormous heat while running. If that heat isn't removed continuously, temperatures rise, performance drops, and stable operation becomes difficult. On Tsubame 4.0, both the CPUs and GPUs, which generate the most heat, are cooled by direct liquid cooling. Cold water runs through multiple pipes lined up along the back, which are then connected to piping under the floor. Heat from memory and other components is released through air cooling. The front surfaces of the nodes are covered by fans, and radiators are installed indoors on the back. The entire cabinet is elaborately constructed so that air flows from the front to the back, and the system as a whole is designed to ensure stable operations with a combination of air and liquid cooling. Tsubame's unique philosophy is not only in hardware, but also in software and usability. The concept is a supercomputer for everyone. At the Institute of Science Tokyo, students have access to Tsubame 4.0 from their first year and can actually use this supercomputer. The computing capability of this supercomputer is embodied not only in terms of performance, but as a resource that can be used in research and development. As such, this capability is referred to as compute resources, which are allocated to users as required in a framework characterized by shared usage. The efficiency of Tsubame 4.0 improved with the scale of use so that compute resources could be used not only by specialists, but also by students and other beginners, and it was designed so that many users could use it simultaneously. Usage methods also evolved so that the system could be used with just a web browser, and it was designed to allow smooth access to compute resources by new users as well. This design philosophy has continued from the era of the Tokyo Institute of Technology, when operation of Tsubame 1.0 began. Tsubame 1.2 was an early pioneer in building a large-scale GPU-accelerated supercomputer, helping the Tsubame series stand out worldwide. Global-scale climate change simulations, molecular design of new drugs, virtual reality, and AI technologies. These other research fields could never have existed without the power to rapidly process huge volumes of data and complex calculations.
In our research group, we are developing a large language model called Swallow. We've been using Tsubame for a long time. This is actually why we can train these very large models easily.
Ryo Yokota, a professor at the Supercomputing Research Center, Institute of Integrated Research, developed Swallow, a large-scale language model that can be used in an open environment. It maintains high performance in English while demonstrating strengths in Japanese as well. Large-scale distributed parallel computation technologies researched over many years have been applied to the scaling and distributed processing of deep learning, with improvements and other modifications to enable more efficient operations. Asako Kanezaki is an associate professor at the School of Computing.
That's where Tsubame's computing power really helps. Because we can run many jobs in parallel, experiments that used to take about a month on our lab's GPU servers can finish in just a few days on Tsubame.
She is expanding research to include the creation of a navigation framework to integrate an understanding of the 3D environment, object recognition, visual input, and language, with a focus on computer vision and robotics. The Tsubame 4.0 continues to evolve as a platform for advanced research that supports the future of society. We will continue using its overwhelming computing capability and flexible usage environment to take on new challenges in science, industry, and society, helping push forward the frontier of human knowledge.